length, we use two different methods. The first method is when curves are defined by functions. So let's have a look at this example here. What is the length of arc given by the function y equals 2/3 x to 3/2 from x equals 0 to x equals 3? And that's a multiple choice question, so we have a few answers. So there is the inbuilt feature in calculus, and if we scroll down, we have the arc length, which is b. The syntax for the arc length is we just enter the right-hand side of our equation, which is 2x to the power 3 on 2, and it was 2/3 of this. And the variable is x, and now we enter x varies from 0 to 3. And when we press enter, we get our answer 14 on 3. So because we have a function here, we enter the expression, the right-hand side variable, and the length of arc. So going back, we can see that the correct answer here is C. The second example is with the circular function. Sophia designs a vase which is based on a solid of revolution generating by rotating this curve for x between 0 to 12, and we rotate around the x-axis. We assume the measurements are in centimeters, and we wish to find the distance around the outside edge of the vase, and the answer is required to 2 decimal places. So if we enter the equation in the graph page, our equation here is 2 sine of pi multiplied times x and divided by 12 and plus 3. We might restrict the domain just to only see this part of the curve which we are interested in. So this is 0, x is less than 12. And that's our curve. We'll change the axis to see more of the curve, and we're going to 12, so let's say make it 15. So if we rotate, we get the curve which is the reflection in the x-axis. So I might just go minus f1 in x. So we'll get the second half. So the vase is having this edge here, the other edge there, and those 2 vertical pieces. That's what we consider the outside edge. So in this case, we need to find twice the arc of length of f1 in x between 0 and 12, and double f in 0 and double f in 12 to add all those lengths. So let's try to do it in the calculator screen. Again, menu, calculus, arc length, and our function is f1 in x, which we already defined, so it comes bold. Variable is x, and we go from 0 to 12. And as we said, we need to double it because we have 2 pieces up and down. And to this, we need to add 2 f1 in 0 plus 2 times f1 in 12. So the arc length of our curve, as we look at it, this plus that and 2 vertical pieces, will be equal to 37.57 centimeters, correct to 2 decimal places. The third example now is when the curves are defined by parametric equations. in this case, we have to use the formula. We cannot use the arc length because it only works with functions. So here are parametric equations for a point moving inside the bigger circle, the smaller circle moving inside a bigger one, and we create a curve, and we wish to find the distance traveled by the point between times pi on 12 and pi on 4, and we want the answer to 2 decimal places. So let's see how the curve looks like. So if we get the calculator screen, the graph screen, we need to change the entry to parametric. And our equations are 5 cos of t minus cos of 5t. These are the x values. And y in t is 5 sine t minus sine of 5t. And we keep the period because it's 2t. So that's a curve. And now if we use trace, graph trace, we can see which particular arc length we are after. So let's say if we go from pi on 12, so it's somewhere here, to pi on 4. So it's up to here. So that's what we are after. We wish to find this length of r. So our function is already defined as x1 in t and y1y in t. So now if we go to the calculator screen, we need to enter the formula for the arc length, which is a definite integral, and it is from pi on 12 is the lower limit to pi on 4 is the upper limit. Now, if you remember the formula, we need to have the square root of dx dt squared and dy dt squared. So let's take a bracket here, use the template to get d in t off, and we can grab x1 in t from variables, and we need to close the big bracket here and square it because that's our dx1 in t squared plus, and repeat that for dy. So again, use the template here, and that's with respect to t. Our y1 in t is there, and again we need to close this bracket here and square, and with respect to t. And then we get the length of arc as 4.33 to 2 decimal places. So entering that is a bit tricky. I have prepared notes pages where entering those equations will be a bit easier. Page 1, 2, and the curve is given in parametric mode, and page 1, 4, when the curve is defined as the function. So what's done here is that we actually define the derivative of x1 in t and y1 in t, and we define the limit. And of course, when we press here, we get the answer. Changing the limits, if let's say I get to pi on 6, we'll of course change this value. And similarly, we can change x1 in t and y1 in t to whatever the parametric equations are, and then we'll get the answer very quickly. So that was our curve. And now this page allows you to find the arc length when the curve is given as the function. So again, for this particular curve, it would be 13 on 12. Changing limits, if I go to 5, will of course change those values as well.